Thank you, Mustafa. Okay, so using that as a jumping off point, I want to talk about the previous semester's work in terms of collusion, oscillation, and how the two intermingle into something really interesting for our project. So the previous semester worked on a bunch of stuff involving collusion. Now, what is that? That's when a bunch of miners pool their resources to try and manipulate the blockchain protocol to suit their own ends. Now, what does this look like? What this looks like is a bunch of miners basically trying to collude, as I said, to decrease the base fee. They do this by publishing a series of blocks below the target gas, for example, empty blocks, for the purpose of driving down the base fee as low as possible. Okay, so knowing this, the previous CAMCOS team basically built a collusion simulation scenario using a constant demand framework, subsetting a certain group of miners, namely 30% as colluders and the rest as non-colluders. And what they found from this simulation is that over time, the base fee is gradually decreasing, as well as colluding and non-colluding miners, revenues are increasing. Basically, from a practical perspective, what this means is that miners are going to collude more and more over time because the pricing mechanism rewards it. And expanding on this, I wanted to expand the simulation to 10, 60, and 80%. And what I found is that there is no effect of diminishing returns. The higher the level of collusion, the better the rewards for all the miners involved. Something I want to point out is that the base fee is decreasing steadily over time, and the short-sighted miner revenue is increasing over time at 10%. It just looks stagnant in comparison to the other two. The next question I want to moving on to like our original work with this project, I want to compare EIP 1559 before and after. Basically answer the question, was the change EIP brought to the marketplace good? Expanding on this, we're going to analyze a bunch of different metrics pre and post EIP 1559 and analyze how EIP handles this traffic in both scenarios. Some of the metrics that I'm going to be studying are the gas prices in the blocks and the relative fullness of the blocks. And so this is the first metric that I'm going to be studying, which is the gas prices in the block, both in the first day of EIP 1559 and in October. So we see the gas prices are dramatically reduced post EIP 1559 in both time frames. Although the two distributions converge a little bit once we get to October, regardless, it's still drastically reduced with EIP 1559's implementation. The next metric that I want to study is the relative fullness of the blocks in both pricing mechanisms. When we analyze pre-EIP, we see that most of the data, or the data is skewed heavily to the left. Most of the blocks are on the fuller side, and the empty blocks are so infrequent that they're basically invisible on our graph. We should note that there should be empty blocks, but due to the way the algorithm has been kind of set up, where I'm only grabbing a random 5,000 observations, they don't show up here. Analyzing post-EIP, we want to note that the distribution of pre-EIP relative to post is extremely tight, which is going to become more obvious in a future illustration. Moving on to post-EIP, I want to illustrate that the skewing of the gas is essentially reversed. Most of the blocks are now on the emptier side, with a little bit more than 1/5 being towards the block gas limits. And this graph basically illustrates how condensed pre-EIP is compared to post-EIP. I want to note that the orange spike that you're seeing is the entire histogram of pre-EIP 1559, basically stuck in that tiny region. Another interesting note is that despite the fact that post-EIP is so much more varied, on average, the gas used is actually slightly higher than pre-EIP. So even though there's more traffic in the framework, it's actually handling it better.